Question.
What's the question you sit out of the way?
Question is, how is it that rockets can actually go forward in space when there's nothing out there for them to push off of?
I've never actually thought about that.
Equal opposite reaction.
Okay, what law is that?
It's Boyle's law.
The third law, yeah. It's kind of interesting. If you go through the momentum chapter in your book, you'll see an article by the New York Times where they, in the early 20s, before people started sending rockets out into space, they were kind of demeaning people who thought that would work because they thought that you need something to push off of, when in reality you don't. It's the action of expelling the material that makes you go forward by Newton's third law. So they were wrong, and rockets actually work. So it's a Newton's third law thing.
What about Cook's law?
Cook's law?
Yeah.
I'm not familiar with Cook, but I'd like to meet him someday.
Captain's
Oh,
company?
Hooke's law? Well, he's the spring guy, and he's cool too.
Captain's.
And if we sent rockets up in space with springs, then I'm sure he'd have something to say about it.
What do you like? Would you be like, that's unethical? Or would you be like,
He'd probably think that's the only way to go. So,
Take a big swing, you can have Dude, that'd be a pretty long swing.
that would be a very long slinky.
it'd be kind of cool though.
I feel like you'd be the person to try it though.
Oh yeah, I would definitely try it.
It's like, go for it. I support it.
I will. And
We'll
if-
create a GoFundMe.
Okay, let's do that. If I get a chance, I might need some help with that. You guys would be right on the top of my list.
Can I ride this Slinky for the moon?
Sure.
Then I'll definitely help.
So, we're starting our next chapter today, and I forgot all about the summary, so we'll just skip it, I guess.
Let's go.
Not necessarily for you at home, because, that's just this year. Potter, you don't have to worry about that. No summaries. So, we're starting Momentum and Collisions. So title your notes, Momentum and Collisions. We'll begin this today, and we'll be doing this over the next couple days.
Yeah.
I thought of the summaries last hour, 20 minutes before I came here, and I was like,
There was 3 on
I
the
really hope he wasn't having us do it. So I texted Lydia and I'm like, it's not there, so I'm not doing anything.
Good call, good call. No need to panic.
I guess. I'm guessing. But it was like a very educated guess. It made sense.
How educated are you guys? Are you smarter than a fifth grader? Kids at home, are you smarter than a fifth grader?
You can start with this.
Well, what if, just a thought, every day you have a class that will scream out a random question in the back, and to make sure people watch the video, it's at a random time every day, and to make sure people watch the video, they have to answer the question.
Guys,
That'd be fun.
Sometimes it could be at the beginning, sometimes it could be at the end, you'll never know, but they have to answer it.
That's a good idea. I think I should try that.
Just thought you guys should know, I found a dryer sheet in my sweatshirt.
Where did Placido find his drag? That could be today's question.
Oh, we know you smell good today then, Placido. That's good.
No,
It's always a plus.
yesterday, so I don't even.
Yeah,
Actually, no, I feel like this was washed a while ago. I
Little
just
horse
never
effort.
worn for a while.
After this class, I'm going to run my car gradually.
So, why is this kind of a little girl?
I don't know.
Alright, I should probably copy this down. Hold on.
Remember the thingy where it's IJK. I like the secret.
Ah, got him.
Does that mean he actually met him here?
That's exactly what that means.
Yeah, probably.
Ha! That's great.
What?
Momentum in the X direction is always imaginary. You guys didn't know that?
Don't worry about it.
Momentum
You're
isn't
fine.
real.
It's just
It's-
the Sieverts. You're good, Sarah. Don't listen to that.
You need some more Sievert sense. It'll bring you to that next level.
Oh, it's the new.
Oh!
You guys notice that the picture of the Sievert Sense candle is the school aging home page?
I love that.
So you know how I was gonna get you that Christmas? Now I can't because
What's the F21?
You'll see.
Okay.
I will explain.
No, I had expired milk this morning. Okay, it wasn't expired, but it. Okay, so we've got the milk. It expires on Saturday.
Okay.
I took a drink of it, and it tasted bad. And then I made the mistake of smelling the carton.
Yeah, that's the worst. Like when you look at the expiration date and you're like a day away, and you
But
open
was
it
like
up to
3
check,
days.
it's like
And I actually like
Heart
took
gets
a big
pounding.
Chug of it because it was chocolate milk, so I was like, oh, this is gonna be my breakfast.
oh,
Yeah.
chocolate milk usually don't smell too much. That must have been
Right.
really old, huh?
No, it didn't. It expired on Saturday.
Oh, and it didn't smell.
No, it did.
Oh.
Okay, so the date of the carton
guys.
is 12/12/2020, right?
Okay.
Funny story.
I
And
thought
I was like, I have 3 days. This will be my breakfast, a glass of chocolate milk. And it didn't taste
Did you
right.
say milk?
No. And I took a drink. It didn't taste right. And then I smelled the carton, and it was sour, but like really bad. Not chunky sour, but sour.
Okay.
Have you guys seen The Office with Kevin's chunky lemon milk?
I don't remember that
When
one.
he added lemon to it so that it cauterized.
I don't have time
He
to
was
watch The Office.
drinking Andy's milk that he left there the whole time he was on the boat trip. Like 3 months.
Okay,
Kevin's
guys,
been
we need to
taking
get back to this.
So let's take a look at this real quick, and the folks at home are going to see it for the first time. So momentum is a nice, easy, simple equation. It's equal to mass times velocity. No fancy 1/2 mv squared, mgy, gmm over r. There's one thing that momentum is equal to, and it's mv. No, not ma. It's mv. Although ma comes into play here, right where you would least expect it.
That's funny. 'Cause
Oh, I wish the folks at home could have seen my face. So, for momentum, it's conserved, and it's conserved in every single direction. So you can do a momentum problem three-dimensionally if you really want, because it's conserved in the x, y, and z direction, and this is just a little reminder of your component notation. ijk is equal to xyz. For this up here, Newton's third law is going to come into play shortly. All this is saying is that force of 2 on 1 plus the force of 1 on 2 is equal to 0, because they're equal and opposite. Hence Newton's third law, the way you guys answered the question today. So these are your basic momentum equations here. Your total momentum is equal to the combination of the momentums of the two objects. And your starting momentum is equal to your ending momentum. This is a good place to start all the problems in this chapter. Conservation of momentum, similar to the conservation of energy, except it's always here. One thing we're going to learn tomorrow is that energy isn't always conserved. There's times when it's lost due to heat or friction. That happens when you have something called an inelastic collision, where objects stick together. But momentum is always conserved, even under those conditions. So, mv is nice and easy to remember. Keep that in the front of your mind. Now, this is kind of a fun part. Force does play a role in this. You can write this down.
Oh, man.
Yeah, I think this is on your formula sheet too, though. So average force is equal to change in momentum over change in time. And what that means then, we can kind of take this another step further because we know calculus. What that means is that if you're looking for actual force, the specific number, that's equal to the derivative of momentum with respect to time. Whenever you've got an expression like this, if the derivative looks like that, derivative of p with respect to t. There's p and there's t. Yes?
Is that why slope is change over y over change over t? I mean x, and that's y over dx?
Well, that's just slope. I mean, derivative would be... I don't think that would play in. I'd have to think about that a little bit harder.
Changing y over t.
It is, that's true. But I don't think you can take the derivative of slope. I'd have to think about that more. It's a good question, though. But yeah, when you've got these relationships, like velocity is equal to change in x over change in t, velocity is equal to the derivative of velocity of x with respect to t. So the same relationship is here. I just kind of want to show you real quick what comes out of this. So if I'm taking the derivative of momentum with respect to time, what's momentum equal to again? MV, very good. Nope. No laughing.
Ha ha.
Hey, So, derivative of momentum is the derivative of mv. So, where's that going to lead us? What would the result of that derivative be?
Second derivative.
No, just the first.
That would be
M would be a constant. It's not changing.
Oh,
So it's a-
oh.
acceleration.
Oh,
Yeah.
ah,
That would be
aha, that's why he's
So momentum is ma. Ma is the something of.
Oh,
So, yeah.
aha!
Momentum is just going to be equal to the integral of
I am
force.
not okay
Like what
today.
Seth said. So, all of physics, all these equations are interdependent. They're a nice big circle, and they're all related. And this is a prime example of that. Basically, what this means is that momentum is kind of an extension of force to an extent. So,
To an extent.
yes. Let's go ahead and do a couple examples, and then that'll be it for our introduction to momentum. Couple scenarios. I think I heard Jaden's getting married.
Oh, my mom is though.
Oh, that's right, yeah.
I was talking about it now pronounced Professor Larry.
Now pronounce what?
It's a movie with Adam Sandler.
Oh, nice.
They talk about circles.
That's it.
Well, you see, what it is,
So is
it's,
a
Kevin,
line.
it's Kevin James, and
It's
the white guy,
ice.
and he wants Adam Sandler to
Ice, ice,
receive
baby.
his benefits, so they pretend to be gay. And then they talk. Joke.
Are
Whoa,
you okay?
All right,
let's get.
here's our scenario.
It's a big.
We've got ourselves a baseball shooting machine here.
Oh, okay.
So draw yourself a baseball shooting machine.
Did you put it on ice so there's
Can
no
we make it
friction?
one of those
Yes.
Gotcha.
That's what I was thinking. It was a pea shooter.
No, wait, is it really cool? It's a
Do you
pea
know,
shooter
it
from
looks like
Transformers.
that one, a character.
Yeah, a pea shooter.
Oh, is that what they're called?
From Plants vs. Zombies?
Sure.
Yep, that's a pea shooter.
He's shooting the peanuts. Well, wait, you can't plant on ice.
Power current barrel.
Oh, this is really sad. Oh, it's not bad, I guess.
So mass.
Wait, doesn't ice like have a view of something? Like very minuscule, but it's something.
You know, the
You don't
action
care.
seems so very easy.
I care.
Yeah,
So
I
far,
care enough.
just
My
Stop
ultimate
here.
life
Stop
goal
here.
is to be able to draw like Mr. Happily. One day, Mr. Happily.
That shouldn't take you too long. Wait till I have to draw a car for the next example, and we'll see if you're still jealous.
Are you gonna do
You
the?
probably will be.
4K
Like, this is so bad. Draws a perfect car.
Draw the Ghostbusters movie.
Is this B for the baseball?
Yeah, B is for ball, P is for pitching machine.
Ah, gotcha.
It took me so long to pick up on this. I remember the first time we used it. Like MD. Like I was spent like I could like 20 minutes trying to figure out what D was. I eventually asked. He's like, "Oh, it's dishwasher or something like that." It took me-
What?
It's obviously a dishwasher.
Right. But it was like a word problem. And it did talk about dishwasher, so whatever it was. It just took me like 20 minutes to figure out where this D came.
Don't you hate that?
Dude, it was, like now I understand when you do it, but it just
And are we finding the velocity of P?
Yep, so yeah, that's exactly what the next question would be. What do you suppose we're going to find? Well, if this is shooting the baseball to the right and there is no friction, the baseball pitching machine is going to go off to the left somewhere. So our goal is to find that
Oh, and
velocity.
because 15 times VP plus the other two equals 0, you can find it easily, right?
So
that's what I was thinking.
Best place to start, bless you,
Plus,
is to just start here. Original momentum equals final momentum, and let's see where that takes us. So we've got the original momentum of the pitching machine plus the original momentum of the ball is equal to the... You guys okay?
Yeah, we're good.
All right. So there's your equation. All the momentum at the beginning is equal to all the momentum at the end.
Oh, because it says EP.
Oh, I get it. So the first PP is going to drop out because there is no starting velocity. The pitching machine and the ball start from rest. So that's 0. The second PP is something we're going to have to solve for. But the first PB is also going to be 0 because the ball also starts from rest. So now,
Just a peanut butter sandwich, no jelly. Oh my god. So P equals the opposite of P.
yes.
So I did spell right away.
Good. Yeah, I'm just spelling the whole thing out. So, in order to do this, then I'm going to go ahead and move the PP to the other side, and that's going to make.
Negative PP
The opposite.
It's poo-poo.
I wonder how much you guys can hear at home. What's going on behind you? Because the more you hear, the worse.
I'm literally crying.
Yeah, me too.
P1 and P2.
We're mature, I promise.
Guys, I'm almost an adult. What are we doing?
The fact that was the first.
Hey, I'm only 16.
So, here we go. If we want to figure out information about PP, we'll just make it equal to the momentum mv.
We don't even need that. Come on. We make our own.
Wait. Okay.
Bazinga.
Alright, I understand that.
So in the end, we're looking for the velocity of the pitching machine. So everything else goes over there. Oh man, you guys are gonna lose it when I show you the preview to Shanghai Noon. That'll come tomorrow or the next day.
Oh,
Maybe today if.
We can get it together.
Yeah, I don't know if we'll finish in time though. So that'll all be divided by the mass of the pitching machine.
Very disappointed. Hope you get it wrong.
So you plug those numbers in, out will pop an answer. Mass of the ball, of course, is 0.15. Mass velocity of the ball is 36, and you divide that by the mass of the pitching machine, which is 50. You should end up with an answer of negative 0.108.
And the negative is just direction.
Yep.
Yeah.
Normally when you write an example on the board, I don't understand it for about 2 weeks, but I think that makes sense.
Is that because of the PP?
I think that is why.
Okay.
The poo-poo plus the poo-boo.
I'm going to go ahead and erase this before we go further into the abyss.
See, I didn't think of I thought of pop for some reason because if you rearrange, if you do P-O of the P, then it's pop.
So let's talk briefly about impulse.
Oh boy.
It's impulse.
Is it this new section or is this the same?
This is the same thing. Impulse has to do with momentum and collisions. All impulse is it's equal to your change in momentum. And that is all. But that's also equal to a couple things, as Seth foreshadowed at the beginning. Yep, because in the same way that when you take the derivative of momentum, you get force. If you take the integral of force, you get momentum. Impulse, more specifically, it's a change in momentum. So Yep.
You said this test is after we come back?
Yeah.
This more relates to work.
That's it. Good. Nothing else really.
So again, looks confusing. It looks like calculus. All we're saying is that in the same way that momentum, in the same way that force is the derivative of momentum, momentum is the integral of force. It's that two-way relationship. So something I want to have you write down then is just what this would look like graphically. That is this right here. Take a little bit of time.
Oh, we learned about this. We solved one problem, never talked about it again, and it wasn't around the quicker test.
In what, calculus?
At least I don't remember.
Wait, what?
how the derivative can all be put in the way I use this as average.
Oh yeah. Got you.
Like, I don't remember anything about it. I just
Average
remember
value,
that. I
yeah.
just remember specific there.
Yes. So it's
That's the only
in
thing I
the
remember. I don't remember how it works or why it works. I don't remember.
Got you.
Pretty much sums up my answer.
That's a good color.
Shut up.
Wow.
Now, if they can't hear that, they're gonna think you're schizophrenic.
Won't be the first time.
In the videos that we watched virtually, were you in the room by yourself?
Yes, I was.
Because I thought it was interesting because you seemed to still be like looking up at a classroom.
I
And I was wondering if you like brought someone in just so you could talk to somebody. But
We
no,
asked
it's
him
just-
if he brought in
That's-
stuffed animals.
No, because
See-
I legitimately, that's what I imagined that he did.
If this was a long-term thing, we're out for like another month, I would bring things in that I could look at.
Yeah.
It's just it's so different when
Make a
you're not
difference in
talking to
pictures.
anybody.
Yeah, you
So
were
I was like imagining you guys in the audience.
Because that was the one day that I was back and you weren't. We talked about that.
What did you imagine?
Sorry,
he
I'm
said?
behind.
That's what I was curious about. What did you imagine last
Was I in the audience?
Oh, you were there, Placido.
You just might have been outside.
Well, that's better than the first one.
What do you mean? The first one was perfect.
Why is it shaped like?
It's an aerodynamic. It's a
Oh
reverse
no, is it
function.
gonna crash?
Yes.
How many people are in the bus?
Nobody that we care about.
Can you put me in the car?
So that all the
So there's no
Me?
one.
see that. It looks like a shoe.
Hey, be quiet. What?
Dude, it's like the wheelies. Yeah.
It's heels.
Wheelies, that's pretty cool.
Yeah.
Oh, I like it.
You know the best part is I'm gonna have to do this in
Oh, really? You guys
So
see
whatever
that?
my car ends up looking like, it's gonna look like heels with an extra wheel.
I'm just gonna draw a box because I'm not.
Wait. Oh, I thought in box, but
So you
cart.
have some boxes
Are you guys done drawing the pictures up here?
Yes.
Okay. So let me just talk about this quick before you draw my amazing car. So when you're doing the estimation of impulse, it's just average force times time. So graphically, it would be equivalent to drawing your line kind of halfway up that picture there. But of course, generally we want to be more specific, so we would actually calculate that integral, which is seen right here.
Say it's in reverse.
And those of you at home, you might want to pause this. There's that one. And there's that one.
Moment of truth. Turn
The best
and I'll
way to
pass this class.
improve
How good
cars
is my
is to
car?
add a window. If you add a window, it improves the car.
That's a fair assumption.
That's true.
If you like,
I'm not going to chance it, though, because if it gets worse, well.
look at mine.
It gets worse than just a race window.
You can just imagine my car goes.
Draw a triangle in the middle of it.
I like mine is the best, but yours are very, very.
Now, if we want to solve for something here, we know that the car begins by traveling at negative 15 meters per second to the left. At the end, it's moving 2.6 meters per second to the right, and that is after it collides with the wall for 0.15 seconds. So what we want to figure out in this problem is the average force that is exerted on the driver. And he's wearing a seatbelt, and there's an airbag, so he's just fine. So, in order to do this, we want to make sure that we remember what all of our equations are. So maybe take another look at your force equations there with momentum. Force is equal to your change in momentum over your change in time. So all we're going to do is do this. We've got all the numbers. So this would be equal to mv minus mv original, all divided by the time. So then it's just a matter of plugging those numbers in. Our mass is 1,500 kilograms. The final velocity is 2.6, and that's a positive number. I'm going to put a little I next to it so I remember we are in component notation here. And when you do that relatively straightforward math, you're going to get yourself an answer. And that'll be 176,000 newtons. And of course, because of the velocity direction that's given to us, it's in the horizontal direction, that means that our force will also be in that direction as well. So just kind of wanted to make sure we didn't forget about component notation there. Questions on this example? So again, this is an estimation here, because obviously the force is going to change as time goes on. It's going to be greatest in the middle of this period of time. It's going to be less at the beginning and at the end. So it's an estimation, and once again, we generally want to be more specific than these estimations. Hence the next example. Goodbye card.
Wait, hold on.
Sorry.
176,000 now.
Yep.
You got it. It's all good.
Mr. Hadley,
Yes.
can we integrate your shark into one of these problems?
Yeah, we can do that.
Change whatever the next equation says shark runs into something. And just shark.
So, a shark is providing a force. And this is no garden variety normal shark.
Oh no, he's got it
Get
better.
real.
Ah!
Oh!
Oh! Is that a whale shark?
No.
What's the mouth?
Looks like it's probably a mako, my guess.
It just, how it's melted, it looks better than just like the regular.
Now this shark
In that way.
is producing a lot of force. And it's not any kind of normal force because it's not any kind of normal shark. Normal sharks don't sit like this. And they don't usually shoot balls out of their mouths like this one does. So it's providing an inconsistent force. It's providing a force that looks like this. It changes over time. It's a little baby shark, so it's only 2.3 kilograms.
Oh my goodness.
It's a lot more for little shark.
I'm wondering if you'd catch up on that.
I'm curious, what did you have the original problem being?
What was it before the shark?
Yeah.
I actually don't know. I think I change it every year.
Oh.
Perfect timing.
So, this baby shark has this force. And our goal in this problem is once again to figure out exactly how fast it's going at the end. We don't have a final velocity. That's what we got to figure out. So, if we want to do this, you might be thinking, why not just start here? After all, we've got a mass, we've got an original velocity, so we should have two of the three things here, right? MVO equals MV. We don't have this. But remember that momentum and force are intimately connected. And if you've got a changing force, your momentum isn't going to be the same either. So we can't do this. We have to make use of our calculus knowledge. Sorry if you wrote that in pen.
Got him. Got him.
So impulse is equal to change in momentum, which of course is equal to our integral of force with respect to time.
Oh, perfect.
And here's our plan then. impulse does not just equal this from the integral. Once we have our change in momentum, that's also equal to mv minus mv original. So if we can use this integral to get this value, and we've got all of these numbers except 1, then we can solve for whatever it is we're missing. And that's our goal right now. So we have to integrate. And we're integrating from 2 to 3.
Oh yeah.
So what's the integral of 2t squared going to end up being? Very good. Linus, what was this one? Yep. Very good. Excellent. So yeah, all you're doing is increasing the exponent by 1, putting the inverse of that new number out in front. That's where that comes from. So, all we do then is we plug in the 3 for all these t's, and then, I suppose I should write it out, shouldn't I? No?
I mean, S.
I'll put it in. I'll
Not
do it.
calculus people.
I'm going to guess it takes me less than a minute. Time.
It'll be okay, yeah. That's a lot of time to keep it. Put the original into the integral setting. Yeah. Or if you have fancy calculator, you just
There.
calculus.
27.
Okay, good.
That was like 29:37.
Sweet.
I'm like, a minute was
So
a
it's
lot of
definitely
time.
26.
So you're plugging in the 3's wherever there are t's, and then you're plugging in all the 2's wherever there are t's.
Counter, look at the clock.
And you take the difference between those two numbers. Once you do that and you get your answer, that final answer is going to be equal to negative 3.14 meters per second, which means our friend the shark, in the end, is moving backwards pi. Yeah, so he's moving in the negative direction, which would be towards the origin or wherever that location is, at 3.14 meters per second. All right. Questions on day 1?
We saw it in
How much
solve
harder does it
for
get?
Original velocity.
Well, that's
Or
given.
Final velocity. Because you have to plug it back.
Oh,
in.
right. Oh, gosh. I totally skipped a part. I'm sorry. Yeah.
I forgive you.
I was
So-
going to
Because
say.
I'm sitting here
This
like,
is-
what
I'm
don't
like,
I
why do you have,
understand?
yeah.
I would have been completely
Oh,
fine. I
boy.
would
You could have just moved that with your life.
I would
Goodness.
one
So this ends up being, negative 1/3.
It's the final.
That'll be the
answer.
final answer. And the units on momentum or impulse is simply kilogram meters per second. And the reason for that is just it's mass times velocity, kilogram times meters per second. So, I'll change colors here. Yep.
I'm the only one who just didn't notice that. He just completely. Okay. Thanks, man.
Yep.
Yeah. So that's just going to be equal to that there. So if we want to isolate this velocity here, thought there was something underneath it. There's not.
I did the same thing.
So used to drawing something in the denominator.
Oh, you can in a second.
So there's our equation. If we isolate that velocity then, it's just a little bit of algebra. And once you do isolate it, you will end up with negative 3.14 meters per second. I'll write down the final expression before you get to that point then.
How much harder does this get?
It's not too bad actually.
Yeah, this isn't bad. Okay, you would expect you're gonna get along with it.
So that's what your setup would be for the end of this problem. Do this math, you get negative 3.14 meters per second.
12 hours to less than.
And that is then the end of day 1 of momentum and collisions. Tomorrow we actually do collisions. So look forward to that.
You're good. Don't think about it.
Are we doing anything with the car again?
You're good. Just say
I
Yes.
think we just keep using the shark.
I think that's a good idea.
Or multiple sharks. You know, whatever we need to
They
do.
can collide into each other.
Whatever sharks you have, that's what we need to use.
There's only one way to end this
I
class.
think we should have a car drawing competition.
Yes.
Wow. I was thinking you would take that really hard and send it all
You
the way
better
up.
still be watching.
Fire one at the camera.
I got my water bottle.
Oh wait, no, don't hit the
Have you
camera.
ever
It's
seen
follow.
that, like,
And now the show is over.
How much time do we have?